Hello everyone, welcome to my YouTube channel. Thank you so much for your amazing response and feedback and best wishes. Today we are driving into the future of computing with someone who is being turning quantum theory into tangible innovation, from quantum hash functions and digital signatures to privacy preserving quantum UML models. Joining us today is none other than Jayesh, who is a project engineer at CDAC India and a researcher whose work bridges quantum security, machine learning, and next generation computing. Let's explore how quantum is reshaping our world one qubit at a time. Jayesh began his journey in physics, mastered quantum algorithms, and has contributed to developing secure, scalable, and efficient quantum solutions, from decentralized ML frameworks to hybrid quantum classical systems. So if you are a student who wants to do BTech project or MTech thesis, or if you are in a research task, you are a researcher, you want to do your research work, or you are an academician who want to guide your students, definitely please do listen this podcast from a really practical person who has done so much of work in the area of quantum computing and who is also doing the same work, continuing the same. So not wasting your valuable time, let us discuss with Jayesh. Thank you, Jayesh, for accepting my invitation and joining this session. Can you please introduce yourself?
Yeah, hi. Thank you, Dr. Rajesh, for inviting me to this podcast. Introducing myself, my name is Jayesh, and I'm currently working as a project engineer in the CDAC Delhi. And for my education side, I have completed my bachelor's and master's in physics, along with some projects in quantum technology domains. And I started my journey in quantum computing and quantum information theory since from 2021. And after that, I'm contributing in this field. Yeah.
Yes. Superb, Jayesh. That is good to know.
Yeah.
So, Jayesh, you worked a lot on this particular quantum computing. Now, you please tell me what are the biggest challenges you faced while developing quantum hash functions for digital signature systems, and how do they differ from classical cryptographic methods?
Okay, so if you consider digital signature schemes, there are pre-existing classical hash functions which are well worked as of now, and we are still thinking that it's going to work in the near future also. But what kept this aside is that if there is any quantum advantage or any quantum computing methods in the post PQC era, then there will be some what I can say there will be some problems with the present hash functions in terms of secure and their scalability. So for that reason, we have started one project and we are thinking like can we build some quantum hash function like which tackles through quantum mechanical principle and which will preserve the security if there is any PQC era comes. So during our quantum hash function, like for building the quantum hash function, we have faced some uh, theoretical problems such as the quantum systems are reversible if we know, and uh, and the classical hash function needs to irreversible principality because it works on one way function and irreversible principle. So to accept this situation, we need to transform our quantum algorithms in such a way that it will show one-wayness and also preserve some reversibility. Because if it is reversible, then it will going to problematic in the near future since the hash it adjusts it will be easily decrypted and all. So yeah, there is this one is a theoretical problem that we have faced. Apart from that, to build something from scratch, like there are some quantum hash algorithms that people are working on it, but we have to think on some different way, like how we can improve it further or how we can make it from like a completely different system. So it will be challenging, like to create some quantum circuits those are efficient in terms of hashing and in terms of long hashing messages and all, which we see in a classical hashing domain. So yeah, it's we have to keep in mind that it preserve quantum principle, and it will give our what is say necessary. It will clear some necessary classical hash matrix to call it as a proper quantum hash function. Yeah.
Okay.
Yeah.
How can this decentralized quantum machine learning frameworks ensure data privacy in healthcare while maintaining model performance?
Okay, so in decentralized machine learning, if we see like today's classical decentralized machine learning, those are completely secure. Like there is in terms of security, quantum is not going to include more on that. But where the quantum take place is that the model training and the quantum machine learning part, which is the backbone of decentralized machine learning. So if we saw the decentralized machine learning pipeline, then there is one segment in which there is a sharing of gradients or a machine learning outputs through different systems, like from one central node to another central node, and in which in this between there is some probability of leakaging the data. And if we look into if we look these parts in terms of in from the quantum perspective, then we can see that we can improve this leakage or we can decrease this leakage so that there will be no data loss in the while sharing the gradients and all, and in the quantum machine learning and what is the gradients. And we have also see that there are some data sets, like if we see some complex genomic data set and the healthcare data set, which are in general complex itself. So those are like quite difficult to model in the classical machine learning system, but can be done easily in or in fewer step in quantum machine learning, we using quantum machine learning. So yeah, we combine these two like segments, one which a model complexity and data complexity with some data leakage proofing, and we have seen that there is some advantage in this side also in QFL. So we term it as quantum federated machine learning model. Yeah.
Oh, whenever you are optimizing quantum neural networks using single qubit encoding, what the trade-off exists between efficiency and accuracy across multiple qubit systems?
Hmm. Okay. So the single qubit system is an a work which is done in 2021 by one of the researcher, and we have extended that work in some multi-dimensional feature extraction thing, where we what our aim is that there are multiple features in dataset, and we have to map those feature in a single qubit system, like single arrays of this qubit. So all features are going to map on a single qubit. But the key catch is here. What we have included is that if we implement like more number of complex feature, then our model, like or a mathematical model, truncate those multi-complex feature into a single qubit system, such that it will relate with each other very efficiently, and it has shown us like a better accuracy in terms of multiple qubit systems which are currently present, and in a fewer steps, in a fewer step and a fewer depth in terms of multiple qubit system. Basically, it's a new classical to quantum data encoding feature if we compare with a multi-qubit system. Yeah.
Oh, okay. Jayesh, in your journey from academic theory to applied quantum systems, what strategies helped you translate quantum mechanics into real world solutions? Because people are very much interested in that. How to translate this theory into real world solutions. So, what is your take on that?
Okay, so yeah, as we see, like my background is in pure physics, like I've learned physics and all, and my master's project's in on a completely different side of quantum computing. It's basically on the quantum communication side, like entanglement, photon pairs, and all. So from that to like jumping into quantum computing domain, it's like an not quite challenging, but yeah, more interesting, like a more interesting journey, because if you have to transition from the academics to the some like computing thing, like technical domain, you have to have some programming skills in your what you can say in your soft skills. Along with that, you have to have domain knowledge. If you are going to work in a quantum computing, you have to have quantum mechanics, at least some intermediate level of quantum mechanics understanding, so that you can implement your what you can say theoretical understanding into the coding skills, and you can draw or you can create some better algorithm or some better functionality. And along with this, you have to have something like collaboration skills, because quantum computing from academic to industry is like not the straightforward way. If you have like collaboration skills and your conversation skills, then it will help you to gain more projects hands-on. You can get a more hands-on project through different projects and through different workshops, and it will also uh, easy to transition from the proper theoretical background to the mixture of theoretical and computational skills. Yeah.
That's very nice, Jayesh. In this context, what programming languages did you learn, and what kind of help they have given to you in your career?
Okay. So basically, I started my quantum journey with Qiskit itself, like IBM Qiskit platform, and it's basically run on Python. So yeah, if you are good in Python, then you can easy to like you have free hand to exploring quantum computing, because all quantum computing SDKs, like most of them, are based on Python itself, and there are few which are C and C++. But yeah, if you have Python, then you can free to explore in this like a coding side of the quantum computing.
Okay, that's very nice. So, how can quantum watermarking algorithms enhance digital data integrity in fields like media, defense, and healthcare?
Okay, so the quantum watermarking, it belongs to the domain of quantum image processing, in which we encode our classical image into the using some quantum properties into the quantum space, the quantum Hilbert space side. So what quantum watermarking does is here, like it will using basically it will encode your classical image into the quantum realm in a quantum state, using the fact that quantum systems are non-clonable, right? Because we know that there is no cloning theorem in the quantum mechanics, that those preserve the states such that no one can retrieve the state after it's created. So the basic principle here is the no cloning theorem itself, but we extend this principle and to build some amazing quantum image encoding techniques such as NEQR, Novel Enhanced Quantum Representation, and FRQR. Those two are mainly using quantum image processing domain to encode a classical image into quantum system. And the quantum watermarking does is here, like if we encode our watermarking in the quantum, like using some quantum technique, then it will help us to preserve those particular document, if we consider document, and if we consider some media, so that it will the what you can say, the third party or another person can't retrieve some necessary information, which because those images are encoded using quantum principles and a quantum technique, it won't be it won't be that easy to retrieve those information from it, because if it tries to retrieve those information, then it will either damage the overall documentation part, or it will corrupt the file itself because of this basis state, and changing the basis state because of the non-cloning theorem itself. Yeah.
What insights did you gain while applying Grover's search algorithm to real world data sets? And what lessons can developer learn from that implementation?
Okay, so if we are going to apply the Grover search algorithm into the real world segment, a real world scenario, then first we need to think that the real world dataset, it has to be unstructured one, because Grover algorithm starts with unstructured dataset, and it will give you quadratic speedup only on unstructured dataset itself. So while we are designing the Grover algorithm for a real world system, we have faced some issues with the Oracle. There is one part in the Grover algorithm known as Oracle. We have to build Oracle in such a way that it will understand our dataset, and it will catch some useful properties from our dataset, so that it will give us amplification in afterwards. So to create a Oracle in such a way that all our data information should be encoded in the overall algorithm, it is quite difficult, and we have created some Oracle structures for the same also. And while doing this, we also have to see that if we are going to increase the data set, and if we talk about scalability, then it will going to increase our growth algorithm depth also, which affects our scalability of the system and also the performance of the system. So what we suggest is that before before encoding a whole dataset into the Grover's algorithm, we can do some classical pre-processing such that we can extract some meaningful data from unstructured data set, and that reduced data we can use in Grover system, so that our Grover's overall system or scalability is also reduced, and we can also expect some better result in this system. Yeah.
Oh, okay. That's very nice. How can we balance quantum resource optimization and experimental scalability when designing hybrid quantum classical workflow, Jayesh?
Okay, so to designing classical and quantum hybrid workflow, we have to see that what part we are going to use quantum, and for what part we are going to use classical. So
Classical.
if we talk in terms of machine learning side, then there is no pure quantum machine learning as of now existed. The whole the every quantum machine learning are hybrid itself, because for data preprocessing and for data preprocessing, like starting part, it needs to have like some classical preprocessing has to be done. And if we are going to encode this classical preprocessed data into quantum machine learning model, then we have used some pipeline which encodes our classical feature into quantum features, such that quantum machine learning model can understand those. And for that part, we use quantum computing or quantum what can say technology. And
Mhm.
the results that we are getting from this quantum model are has to be optimized. And for that part also, we are using classical system. Like there is classical optimizers, and so yeah, these are the combination of this, like classical needs to have in quantum machine learning, like hybrid quantum machine learning, so that we can get some better result, and uh, we will retrieve some amazing results from new data set and all, because there is no quantum optimizer itself, and there is no any thing known as complete quantum machine learning pipeline. So yeah, the thing is that we have to choose for what factor we need quantum thing, and for which part we need to classical thing. And accordingly, if we balance this thing, then we will have some amazing hybrid system. Those can work
Yes,
efficiently.
very nice. Okay. This is a very good point you have told, Jayesh. Thank you so much for that. What key skills should young developers build to contribute to quantum information science projects, especially those focusing on efficient quantum resource utilization?
Okay, so yeah, uh, same as previous answer that I give you. Like if you have like a if you want to enter in the quantum computing domain, then you need to have some basic understanding of quantum mechanics itself, because the basic of quantum computing is quantum mechanics. The quantum mechanics principle are going to use in this system. And if you have some linear algebra skill, like mathematical, not that moderate, but some basic matrix and all multiplication, linear algebra skills, then you are good to go from theoretical perspective. But this is not sufficient. Then you have to apply your theoretical skills on the computation level. Then you need to have some programming skills, like hands-on experience with some framework. Just as I told you, like Qiskit, the IBM one. If you have to go with quantum machine learning, then Kenny from Xanadu, it's great for quantum machine learning thing. And there are other SDKs also. The if the as you explore the quantum computing domain, then you can see like there are various SDKs, and you can choose any of them as of your flexibility. And it like it necessary to understand that the classical optimization part and the quantum optimization part are the two different things, and how they are contributing, and how we can add those two things such that our whole proper quantum computing pipeline should give us like better results and all. Yeah.
Yes. Here, how important is this interdisciplinary collaboration? Because you are coming from physics background, and combining this with computer science and with engineering in accelerating quantum technology adoption across industry is very important for any student. So, what is your take on that?
Okay, yeah. So the collaboration is the main thing, and it's a very important thing if you are coming to like not quantum itself, but in normally tech field, like any other industries and all. Because if for example I am from theoretical and like physics background, then I have knowledge of like a theoretical understanding from theoretical point of view, like basic of like including mathematical structure, some principles, some theorems and all. But if I have to explain those for the person who's from another domain, then we have to have some like a link in between, such that the two party can understand their thing very efficiently. For example, the physicist can build a better hardware in terms of theoretical side. The computer scientists or the computational skills people can write the code in better way in if we compare from physicist side. And some engineers hardware designers can build some better chips and better qubit QPUs and all if we compare from the different people. So yeah, the collaboration between these or like other domains can help us to improve our today's quantum computer itself, and also some computation skills also, like quantum computing skills also. Yeah, and open
Yeah, well
collaboration with
said.
and all companies all for example the Qiskit, the IBM's the Qiskit certificate have appreciate the open collaborations in their portal so that people can learn and they can also provide help to the general audience so that the companies and domains will grow eventually. Yeah.
Okay, well said, Jayesh. What do you envision as the next breakthrough that will push quantum computing from research labs into main commercial applications? As of now, still people are thinking that it is a research kind of thing, it is a theoretical thing. But what is the next push that will bring this to commercial applications?
Okay, so from the breakthrough point, I think the fault tolerant quantum computing, which is like proper error prone quantum computing, will be the next breakthrough, which will shows us true power of quantum computing. Without errors and without any difficulties, we can simulate any quantum systems in the fault tolerance quantum computing, and we can we can create some better results from this. And if you know, there is one IBM's quantum timeline. It will also shows that from 2020 till 2029 they will build some fault tolerance quantum computer with some large number of qubit count, which will help us to discover some uh, which will help us to discover, for example, not discover but explore different domains such as drug discovery. It will help us to understand what actually drug discovery is and how the complex molecules can be encoded into quantum systems. Also, along with the material designing, along with some, if we consider proper important domain known as finance domain, it will help us to boost finance domain from the application side to understand how the risk analysis has been done in finance system. And if we consider some security, then it will help us to see the how cryptography can how cryptography can perform using like fault tolerance quantum computing, and how we can took advantage of this quantum computing system such that we can have proper quantum ecosystem in the near future. So yeah, till I believe next 5 to 7 years we can see some major breakthrough in the quantum domain. Yeah.
Yes, that's very good to know. Finally, Jayesh, what is the advice you want to give to the youngsters? Because you know this in universities are introducing BTech quantum computer degree course, MTech quantum computing specialization. So, what advice you want to give to these newly entering students into this field?
Okay, so the first advice I would like to give is that don't apply quantum in every problem statement. See problem statement, if it is showing quantum advantage like in terms of theoretical and all, then go ahead with the quantum, because quantum computing is not built to solve every all the problems
Yes.
which are working on classical. It has to be chosen carefully so that we can see quantum advantage and what I can say, use pure power of a quantum system, quantum nature. Yeah.
Yeah, that is very, very important point. Using quantum for everything is not
It's not.
advisable.
Yes.
Only thing where we get the quantum advantage, we have to apply. That was really awesome, Jayesh, to talk to you. And thank you so much for providing valuable insights and practical insights in this quantum field. Thank you so much, Jayesh.
Yeah, thank you, sir. And I will appreciate uh, I would like to state one statement is that if you are thinking to jump into quantum industry, then do jump, because it's not that there are some various government plans also which are in the quantum ecosystem which are going to which are going to increase the student and the proper skill set which has currently necessity in the quantum domain. So yeah, have a great day, sir. And yes,
Thank you so much, Jayesh. Have a great time and wish you all the best. Thank you.
Yeah. Thank you.